Okay, so if we think about how graph search works, for many graphs, the definition of symmetric, right? We could find paths from the start nodes to the goal nodes, or from the goal nodes to the start nodes. And the second one is we have to reverse the arcs. So that if you think about the graph where with reversed arcs, then you can actually search either way of those. So what we're going to do is to define two things. The forward branching factor is the number of arcs out of a node, and the backward branching factor is the number of arcs into a node. And these can be quite different. So for example, if we have a tree, one of them could be 1 while the other one might be 2. Okay, so now we remember when we do the complexity of the algorithms, the search complexity is generally b to the n, the branching factor for this to the n. And so we should use forward search if the forward branching factor is less than the backward branching factor and vice versa. So which way we go depends on the branching factor. Okay. Sometimes, however, particularly when the graph is dynamically constructed, the backward graph may not be available. So one of them, either the forward or the backward, might be more difficult to compute with the other. So if we have a state-based problem, given a state, it's easy to work out what the actions are that the effects of those. But given a state, it's hard to work out what actions would have resulted in that state. That's actually harder to do sometimes. Okay, so that's one idea, is to actually think about optimizing the direction of search. One other thing we can do is we can search backwards from the goal and forwards from the start simultaneously. This might seem, well, it's a waste of time. However, if you think about that, the search for this can be, each of one of them could do half of the k on 2, we could just do it twice. And it turns out that 2 times b to the k on 2 is much less than b to the k for any reasonable k. Okay, and this actually results in an exponential saving in both time and space. So the difference between these is b to the k on 2. So that's an exponential saving. So we can do, this often works. So bidirectional search is a good idea if we can do it. However, the main problem is making sure the frontiers meet. If you can imagine two depth-first searches, it's quite possible they just pass each other and never meet to each other. So we have to make sure in a bidirectional search that the frontiers meet. So a common way of doing that is using a breadth-first method, for example, least cost first search, that builds a set of states that can lead to a goal quickly. So we're starting from the goal and building the states that go into that. So we're doing that. In the other direction, we could use another method where typically depth-first search can be used to find a path to these sort of interesting states, where we know how to get to the goal quickly. And this is often a very useful technique. How much is stored in the breadth-first method, the one that goes to the goal, can be tuned depending on the space available. So here we can use as much space as we like to work out how fast you get to the goal, and then we can tune that depending on the space. So we can use the fact that something uses lots of space. It might not be feasible, but we can still use it in one of these bidirectional searches. Okay, it's often a good idea to do this, and it often works well. Another idea we can do is to find a set of, so if we find a set of what we call islands. So if we knew we go from S to I1, if you know we have to get to I1 to IM minus 1 and then to G, so there are M sub-islands we know, this can be much easier to solve because M times B to the K on M is much less than B to the K. So we have M problem each of size B to the K is much less than B to the K. Each of them of size B to the K on M. And the problem with this is to identify the islands the path must pass through. And this is difficult when we want to guarantee optimality for this. But often you have a robot you might know that has to pass through particular doors. So instead of searching without knowing that, we can search from where it is now to a door and then from a door to somewhere else. So we can do things like that. Notice that this requires more knowledge than just the graph and a heuristic function. It also requires the knowledge of islands. But if we have that knowledge, we can exploit it efficiently. Okay, and these sub-problems can be solved using islands again. So we can solve each of these subproblems. For example, I1 to I2, we could identify other ones. We get a hierarchy of abstractions in here. And that's often also a useful thing. So there's a whole lot of algorithms that people try to exploit this. Okay. Another common algorithm is what we call dynamic programming. So for stationary stored graphs, what we're going to do is we're going to build a table of distance of n, the actual distance from the shortest path from node n to a goal. Right? This can be built backwards from the goal. So the distance function of n to the goal is 0 if it's a goal. Otherwise, it's the minimum of all the arcs for all nm. We can do this plus 0. And this is essentially just using least cost first search in the reverse graph. Okay, so we're just doing least cost first search in the reverse graph, and we end up with a function that gives us a path from every node to the goal, an optimal path from every node to the goal. And so this then locally used to determine what to do from any state. What do you do? Well, you move to the you move to the goal. If you're at any node and you have the distance function, you move to the neighbor where this is minimum. Okay. Now we can ask in class, why not use A star? Surely A star is better than least cost first search. Something to think about. There are two main problems with this. Oh, well, that messed it up. It requires enough space to store the graph, and the dist function needs to be recomputed for each goal. Okay, it requires enough space to store the graph, and you have to actually have the dist function needs to store the goal.